Okay, hello everyone. It's a pleasure to have here Ruchika today. Thanks a lot for accepting our invitation. Ruchika finished her PhD at Jamia Millia Islamia University in India in 2020. Later, she joined the India Institute of Technology in Mumbai, in India, for her postdoctoral research, and then the INFN at the University of Rome La Sapienza in November 2022 as a research fellow. The research interest includes testing theories beyond the lambda-quarter matter and learning about dark matter and dark energy behavior, and the study of the cosmological tensions utilizing probes of high, low, and extreme zero redshift. Today, she will present reviewing anomalies and exploring proposing new directions, CMB, BAO, and supernovae. Ruchika, you can start please when you're ready.
Thanks a lot, Eleonora, for the introduction and for invitation for this very nice seminar series. And thanks everyone for joining. So today I'll be talking about reviewing anomalies in different experiments in the most precise cosmological measurements such as CMB, BAO, and supernova, and exploring and proposing new directions using some unexpected results from different new probes, new and upcoming probes. So this talk will be based on the work with these people, and so the highlights of my talks are reviewing anomalies with the most precise measurements in cosmology, which is CMB, BAO, and supernova. And I'll talk about the work I've done with challenge and test the standard assumptions in present theoretical models. And we have studied unexpected results from new and upcoming probes. The new probes that I will be talking about is Holy Cow and JWST. And I'll be also proposing new directions to understand the dark sector better. So this is the picture of our universe, and roughly it is at present 13.77 billion years old. And it is expanding and accelerating at present. So this is on the right, we have redshift 0. And we can measure the expansion rate of universe just by seeing the galaxies with which velocities which they are receding away from us. And we can measure the expansion rate of universe. Other way to measure the expansion rate of universe is using the first light from the universe, which is the cosmic microwave background. And just by seeing the temperature and isotropies in the sky and using your favorite model of cosmology, one can actually measure the expansion rate of universe. And assuming that on the large scales, we are living in a homogeneous and isotropic universe, no matter at what redshift and using which probe we measure the expansion rate of universe or the Hubble expansion parameter, it should be same. And so the most important question, using all the probes in between a different redshift, what we are trying to measure is how is the expansion of universes happening, and just inverse of the Hubble parameter at present gives us the age of the universe. So just by measuring the expansion rate of universe accurately, we can tell about how much energy content is in each component of the universe, like how much is the dark matter, how much is the dark energy, and what is the behavior of their interactions. So measuring this quantity or this parameter is one of the most important parameters in cosmology. And right now, the two most precise experiments really measuring from around 2000 is like CMB and like WMAP and Planck. And then we have SHOES around present redshift. And just to remind that when we are using SHOES, we are just measuring from the low redshift, and we are just seeing the recession velocities or around us, and we go far and we are measuring the standard candles and what is their distance from us and their luminosities. And we are not assuming a cosmological model there. Just by using astrophysical assumptions and using the standard objects like Cepheids or supernova, SHOES team concluded that the value of H0 is around 73.04 plus minus 1.04. And early universe, by assuming model as lambda CDM and using the temperature and isotropies in the CMB sky, the value of H0 comes out to be 67.4 plus minus 0.5. And these values they are around redshift 0 and redshift 1100, they are more than 5 sigma apart, which should not be the case because we are assuming that we are living in a isotropic and homogeneous universe on large scale. So this value should not change. And just to see the time evolution of Hubble constant and when did it actually started to become a tension, when did the measurement of Hubble constant started to become a tension. So we see here the time evolution, and the map starts from 2000, and on the y-axis I have Hubble constant. On the x-axis I have the year from 2000 to 2024. But just to be very careful, it is not the redshift, but the year. And on cosmological scale, it is all redshift 0. So this is not the lowering trend of H0 or something. This is just how the H0 was measured from 2000 to 2024. So initially, you can see till 2023, we have no actually Hubble tension, but both the experiments from inverse distance ladder and standard distance ladder, we were able to measure the value of Hubble constant, and they were both agreeing with each other. Only after 2013, we started to get this tension, 2 experiments, which is standard distance ladder, which is from Planck, and inverse distance ladder, which is Planck, and standard distance ladder from Hsu's team. They got more and more precise, and the errors shrink, and that's where we started to see the tension or Hubble tension. And there were not just these 2 probes, these are the most precise, and they have been doing the analysis from really long, but there are many other probes. So this was a really nice paper by Lenora, and she has listed out mostly all the probes, which measures the Hubble constant using the high redshift probes, or we can say the probes which assume some model of cosmology, or we can also say, since we are not directly measuring them, we are using a model of cosmology, and they measure, all of them measured the value of Hubble constant around 67, which is a lower value of Hubble constant. Then when we take direct measurements and we see the objects around us very accurately using some geometrical techniques, and we measure the values to be a bit higher than what is measured from the high redshift observations. And we can see that this band here, this comes and agrees with all the indirect measurements, and this band here is agreeing with most of the low redshift measurements. But this 5 sigma tension, which we are considering, now the question is it between high or low redshift, or indirect or direct? But I would like to believe that this is Planck versus Hsu's, because others' error bars are really bigger, and those measurements are still not precise enough to say it is 5 sigma tension. And also, I have done a work on this in 2019. So while we are saying about tension, what we should not do is we should not include Planck and Hsu's both at the same time, because otherwise all the values will merge. So in this paper, what we did was we used all the measurements in between from baryon-acoustic oscillations, masers, strong lensing supernova, cosmic chronometers, and growth data. And we found out that and we have taken here different models, which is lambda CDM, WCDM, CPL, and also PADE parameterization, which is completely different from cosmological model. It does not include any information about cosmology, like how much matter or dark energy should be there. It is just a better form of Taylor expansion. So it is, in that sense, it is cosmological model independent, and we have used all of these models, and irrespective of the dark energy behavior, we found that the value of Hubble constant that we get is also agreeing with the Hsu's and also with the Planck. So if we take all other probes in between, other than CMB and Hsu's, there is no signal for new physics. So this tension, which say as Hubble tension, is maybe because there's something we are not understanding in the Planck experiment or in the CMB. Maybe also the reason can be that we don't understand the standard candles which are used in the standard distance ladder. Maybe we are not understanding supernova or Cepheids properly. So highlight of my talk, again, firstly, I'll be talking about CMB. So looking at CMB, there was this paper by Holzbach et al. In 2021. So what they did was they take different patches in the sky And you can see here, taking different patches in the sky, they are getting the value of H0 from 76 to 61. So different patches, taking different patches, they get value lower than Planck and bigger than shoes. And they are just using CMB data here, different CMB skies, and when they take all sky measurements, their value agrees well with Planck. So taking different sky and getting different values, maybe this is a violation of cosmological principle, but it has not been tested and can be tested by high quality polarization data. So we should be looking forward to it. And if this is really an anomaly, or it can actually be just lying in the high redshift, and we don't need a solution from low redshift, and maybe we need to be very precise here, then looking with Planck. So this is a really nice picture I like, taken from Hubble Hunter's Guide. So here these more precise probes are there. And you can see this orange band is from shoes, and this blue contour is from Planck. And the H0 value is around 73 and around 67. Also, the RD given by Planck is around 147. But BAO, since BAO measures the same temperature and isotropy scale imprinted in the sky, but at different redshift, that's why we are getting different correlation here, and it breaks the degeneracy. But what we can see here, that Planck is in tension with shoes, but BAO agrees well with CMB and with shoes. But within the Planck itself, when we are taking L greater than 800 and L less than 800, the results are matching like 1 sigma, within they're touching the 1 sigma boundary. But if we see here, for L greater than 800, again, Planck is in tension with shoes. But when we take L less than 800, it agrees well with BAO, CMB, and shoes. So we need to see if what is happening at L less than 800 and what is happening at L greater than 800. We need to really understand the CMB anomaly. And also there's a other CMB experiment, which is ACT, which only uses the high multiple data. So this is paper by William Giare et al. And then they measure the value of, again, they measure different cosmological parameters here. And when the Planck is in tension with X data more than 2 sigma, irrespective of the L values. So you can see here, this is bigger contour while taking just L greater than 650 of Planck. And this is taking Planck whole values, and this is in tension. So seeing these anomalies within CMB and within CMB, different patches of sky, and between ACT and Planck, we must see that how are the results from Planck satellite, and what about the new expected results can say about Planck satellite results. So we see here about the JWST results. So the new JWST observations suggest presence of very high massive galaxy at higher redshifts. So around the redshift of 7 to 10, there were observed very high massive galaxies. And according to assuming lambda-CDM linear evolution and the evolution from using lambda-CDM, we were not able to explain these extra massive or extra bright galaxies. And you can see here that these curves comes from lambda-CDM cosmology. And this, on the y-axis, we have cumulative stellar mass density. On the x-axis, we have the limiting mass. And these are the curves that are coming from theoretical model taking cosmology lambda-CDM. And these are the observations which are more than 2.5 sigma away. Now there's another paper that appeared in Nature, which again plotted the cumulative stellar mass density against the masses. And these two are the observational points from JWST. And this parameter epsilon here, which represents how much baryons can actually convert into stars. So this black curve comes when all the baryons convert into star, which is obviously not possible. And according to the observational constraints, this epsilon is 0.32 is the most highest value which is allowed. So we will say that epsilon 0.2 is around the safe value, so which is again more than 2 sigma away from the JWST results. So we worked on this and we build the JWST likelihood, and there this cumulative stellar mass density is there from JWST results, and we build it theoretically, and using the theoretical part, what goes inside this is the cumulative number density of the collapse objects between mass m and m plus delta m at redshift z. And to calculate this, we have assumed certain term in mass hello mass function, and sigma rz is the variance of linear density smooth at scale r. And we have used CAMP here to calculate the sigma, and then we have used Planck chains, and we have done important sampling to finally calculate the value of a chi-square while using Planck TT plus JWST and different combination of Planck chains along with JWST. So as I said, epsilon 0.2 is like in the middle value, and I would prefer to take this value because I don't want to go to the extreme 0.32. So taking this value, if we see here, the chi-square is around 5, but as soon as we include low E polarization data, the chi-square gets worsened. So in this, taking this, so maybe there's something happening in the low which makes the chi-square worse here. And these are the contour plots of other parameters. So we see here when we are using TTTEEE, the tau parameter, which is the optical depth, is constrained very precisely around the value of 0.05. But as soon as we add JWST data in TT, and taking different values of epsilon, again, I'm considering epsilon equal to 0.2, we can allow tau to take a bigger, higher values of tau. And we can see this in Planck release from 2000, WMAP release from 2013 and later 2018. The mean values of this has changed. And if we see here that low E polarization is crucial in determining the optical depth. And if we see here, it is this low E which is making the tau observations very precise, and JWST prefers a bit higher value. And because of this, the sigma 8 can increase and may be responsible for the higher massive galaxies, which this model like lambda cedium, in lambda cedium, we require higher tau, and which can be explained in the low E polarization. So how much do we already trust this? So because the mean value has shifted a lot, so maybe this parameter we need to really check again. And so the conclusion of this work is the possibility of unknown systematic error in current large scale angular scale polarization measurements, or an unidentified physical mechanism that could lower the expected amount of CMB polarization produced during the epoch of reionization. Another possibility can also be there that it is arising from this JWST measurements. Maybe the IMF they are using is different. And also I've heard recently that the bright galaxies may not be the most massive galaxies. What we are seeing is actually the most bright galaxies, and the conversion is not just straightforward, like the bright galaxies are more massive galaxies. There's much more involved how they take the luminosity function. So we also need to consider that into account. And maybe there is new physics beyond lambda cedium which can explain this. And for that paper, I'm not talking about, but you can definitely refer it to this paper. So there are two solutions where here I didn't conclude which of the, like either there should be something in CMB or from JWST, which is in the low redshift, or we require different model. But again, if there are cosmological tension, I say there are two types of solution, early time solutions and late time solution, then which one is my take and which one I believe can solve cosmological tensions? So in early time solutions, we know we have early dark energy, but that is in conflict with LSS data and weak lensing measurements. And also I've done work which makes me biased towards late time solutions. So this was a very interesting figure in Holy Cow results, and we can see here the value of H naught, and they have taken strong lensing, 6 quasars, a different redshift. We can see, and here it's not the years, but the redshift as I was showing on the second slide. So here we can see a different redshift, we get different values of H naught. So, and they have just used 6 quasars. So maybe there is some systematics there. And maybe since it is one data point at each redshift, maybe it is not very precise, but this trend was really interesting to us. So we wanted to check this trend, and we have taken different, till redshift of 0.7, we have taken different probes like supernova, cosmic chronometers, and BAO and masers, and we have taken different set of data sets, and we bin the data, and we found absolutely the same lowering trend. And this work has again been tested by Maria Deanotti et al. I think, please don't quote me here, but also she has used some scalar field models, and she got the similar trend. So, and then if this trend is true, then just going till redshift of 0.7, we are able to get the value of H naught nearly around like lower value, around 67 for sure. So if this Holy Cow measurements trend is true, and if this trend really holds in the low redshift data, then maybe we don't need to go and increase the value of H naught at higher redshifts. So I'm more biased towards late time solutions, or maybe a mixture of late and early time solutions. But today, I'll be talking about now late time solutions. And late time solutions, what can be done? So maybe there is a recalibration of distance ladder. Maybe the standard objects we need, standard objects we are using, maybe they have some anomalies, and maybe there is some room for change. So before just saying that, okay, let me show my work, what I've done for late time solution, let me first convince you that there are some anomalies in the standard distance ladder, and maybe we need to test them as well. So I'll be talking about these papers now. So this is standard distance ladder, and this is everybody knows. So this is a rung of standard distance ladder, and we have anchor galaxies here. In anchor galaxies, we have mostly MW, LMC, and NGC 4258. We know distances to them very accurately, either by the geometric methods like parallax, or using detached eclipsing binaries or masers. So these are the anchor galaxies, and these have Cepheids present in them. Here we build PLR relation, and we use this PLR relation in the calibrator box. Here, since we know the PLR relation, we know the distances to the Cepheids, and there are galaxies which have Cepheids and supernova in them. So if we know the distances to the Cepheids, we also know the distances to the supernovas. And if we know the distances to the supernovas, using their apparent magnitude, it is very easy to calculate the absolute magnitude of supernova. And then using the Hubble flow supernova, we can calculate the expansion rate of universe. So let me first convince you that why we need to find a solution in the low redshift or extremely low redshift region is that we are assuming the same PLR valid for Cepheids till the entire standard distance ladder. Okay, so this is the picture given by Edwin Hubble when he measured the expansion rate of universe in 1929, and the Hubble law, which is V is directly proportional to the D is directly proportional to the velocity which they are receding away from us, and it was quite valid in 1929 until we have in 1998 we have more observations, and we really need to go till higher redshift. And if we go till higher redshift, even if the order of Z square, we need to have the acceleration term to explain the accelerating universe and not just expanding universe. And this happened in the year 1929 and 1998. But we are assuming the big assumption given by Henrietta Swan-Leavitt in 1908 that the same Cepheid PLR will be valid throughout the distance ladder. I've seen works where they have tested the PLR break on the basis of days, like just 10 days or 15 days, but they have not checked the PLR break on the redshift axis. And this was about the Cepheids. Then another standard objects which are in the standard distance ladder are the supernovas. Now, does this L is directly proportional to the Chandrasekhar mass? This standard assumption that goes into saying that supernovas are the standard candles, does it hold true? Actually, no. There are some papers which suggest there are observational evidence for possible violation of Chandrasekhar mass limit significantly. It could be sub as well as super Chandrasekhar mass. And there was another paper by Wright and Lee where they have done semi-analytical calculations and they have found the inverse relation of luminosity with Chandrasekhar mass. And also there was this another paper which utilizes the Tully-Fisher data, and they found the hints of G-transition at the lower redshift around the same distances which are in the calibrator box of standard distance ladder, and around the same distance where we have Cepheids and the supernova. And about that if G change is G transition or variation of G is really possible, there have been works from really long 1993 and 1983 that explains that the variation of G is there. So let's hint, we have anomalies and now we are convinced that we have anomalies in the standard objects observational data, and we need to test other probes. Like in Tully-Fisher data, we have seen that there's a G transition is possible. We need to test it in the astrophysical objects around the same redshifts. So other objects which are Cepheids, TRGB, and supernova. So today I'll be talking about Cepheids and supernova, which actually build up the standard distance ladder by the Shoes team, and how it will affect the distances inferred in non-standard gravity scenario. So before introducing the change, that what happens when I introduce the G transition, let's see and understand the basic physics of Cepheids and supernova. So in Cepheids, the pulsation of Cepheids, which we use like PLR, from which we build this PLR relation, is related to the astrophysics, and it related to the ionized helium atom. So we can say here, then when we have single ionized helium, it is comparatively more cooler and it makes more transparent than the doubly ionized helium. Just because doubly ionized helium have more free electrons and it becomes more opaque and it is more hot. So we can see here that when it is doubly ionized helium, it is comparatively small and dim. Since it is really heated, it starts to expand. And as it starts to expand, now it is more cooler and the outer layers become singly ionized helium. And since it is singly ionized helium, it is more transparent and it can emit more light, but it cannot keep expanding always. So it contracts again and it becomes dim again. So it goes from series from dim to light and dim because of the pulsation happening inside. So that's why they are known as standard objects, because of this pulsation, and they can follow this PLR relation always. And it was observed by Henrietta in 1908. And if we know that this PLR relation is valid, and we can, for the nearby Cepheids, we know the periods and as well as their apparent magnitude, we can actually build the PLR relation in the anchor box. And using this, we can go to the faraway Cepheids. Now, just by seeing how they are pulsating, we can find their apparent magnitudes. And using their apparent magnitude, we can find their distances. And in supernova, we have white dwarf, which is accreting mass from the binary star. And as soon as the mass limit of the white dwarf reaches around 1.4 solar mass, because of the electron degeneracy pressure, there is carbon oxygen detonation that occurs, and it explodes around the energy of 10 to the power 51 erg per second. And if we introduce the change in Cepheids, there are two phenomena going on. One thing which I will just explain, the pulsation of Cepheids, and also there is core burning. So this is how pulsation will change if I increase the gravity. or gravitational constant. So this is my PLR relation, which I'm trying to build for Cepheids. Now, if there is a scenario where I increase the gravitational constant, so I am at a point A. Now, if I increase my gravitational constant, just by simply using this relation, my pulsation will decrease. So from point A, I will come to point B. Now, what is happening in the core is because I increase the gravitational constant, I will need more core burning to compensate for creating more pressure. And because of more core burning, there will be more luminosity. So the luminosity will increase here. So from point A to point C, I'll reach. So there will be a shift in PLR or shift in the intercept of this PLR relation. Okay, there will be shift in Cepheid PLR. There's a break if there is a non-standard G scenario. What happens to the supernova? Now there is explanation, but I don't completely understand it. So, but for time being, what I do here is there are scenarios which says in standard scenario, L is just directly proportional to MC. And in another scenario, there is that Wright and Lee and other papers, they are suggesting that L goes inversely proportional to MC. So what I did here is take N free and give its prior value to negative and positive. So it can data, by just giving the data, it can take whatever value it wants. So if N equal to 1, standard scenario is there. But if N comes out to be different or negative value, it will support the Wright and Lee values. So why vary N? Because we are from data, we are seeing that L is having inverse proportional with MC, which means standard luminosity decreases with the Chandrasekhar mass. So I will try to incorporate all these changes in the standard distance ladder equations. So these are the basic empirical relation that goes in standard distance ladder. Firstly, I was showing in terms of rungs. Now it is shown in terms of, in terms of the empirical equations. So we can see here we have anchor Cepheids. In the anchor Cepheids, using the PLR relation, because here we build the PLR relation. We know the distances to them very accurately using geometry. And we try to infer the value of BW and MH. So that's why we are saying we are building the PLR from the non-Cepheids. Because if you see here, these boxes, these rectangular boxes are the observables, which is pulsation, how the Cepheids are pulsation, and what is their apparent magnitudes. So these square rectangular boxes are given to us. Mu for the anchors, we know very accurately. We put bounds on slope and intercept of the PLR, and we use that in the calibrator box. Now in the calibrator box, we have already nearly constrained bounds on BW and MWH. We have been given log P and the apparent magnitude for Cepheids. And from there, we get to know the distances where the Cepheids are present. Now in the same galaxies, the supernovas are present as well. Now we know from there, we know the distances to the supernovas, and we can actually put bounds on the absolute magnitude of the supernova. Now in the Hubble flow box, once we know the absolute magnitude, we can calculate the value of Hubble constant very easily. We have used the observational data present for all the Cepheids and the supernovas. And we have used extremely wide priors on PLR slope and intercept and the distance calibrated galaxies. And we have used the Gaussian prior for the anchor galaxies. Before we wanted to introduce G-Transition, we wanted to check what is the value of Hubble constant that comes when we are trying to build standard distance ladder without incorporating any G-Transition, because of course we are not, we are taking assumptions that metallicity is very low and other things. So just that we have not incorporated dust corrections, but our data, instead of taking those assumptions, is in well agreement with SHUS 21 and SHUS 22. So, okay, our standard distance ladder is right. Now let's just incorporate the G-Transition in the Cepheids and in the supernovas, and let's try to see how much it affects our inference of result in the Hubble constant values. So because in the Cepheid equation, there will be two changes, because one due to the pulsation and one due to the core burning, which you can just refer and see the same equation. There are just two components. One is for the pulsation, another for the core burning. And in the supernova, because now the distance inference due to the change in PLR has changed, the distances have changed. So distances before the G transition will be different, and after the G transition will be different. So one of them will have absolute magnitude MB1, which are before the G transition, and after the G transition we'll be having absolute magnitude, which is MB2. And the absolute magnitude or supernovas which are closer to the Hubble flow supernova will tell us what is the value of Hubble constant. So now it will be MB2, which is closer to the Hubble flow, and at the end of the calibrator box, which will decide our Hubble constant. So we have binned our data, and we have taken the whole entire calibrator box from distances 29 for mu 29 to 32.5, and also the box ranges from 28.5 to 33, but there are not much objects to do the survey. That's why we started from 29 to 32.5, and we have taken steps in increase of we have taken increase in steps, how much increase is allowed from 2 to 8%, and we perform the MCMC fitting, and we see the results here. So this cyan, this shaded peach band is from shoes, and this gray band is from Planck. And these are our results. These points are our results for the 40 cases. But with the least chi-square, what I've got is that, and which is saying that around the 4% increase in gravitational constant around a distance of around 17 megaparsec. If I allow that in the standard distance ladder, the value it gets is H naught comes out to be compatible with the Planck value, and the N value, which I left free just to check if the luminosity is directly proportional to the Chandrasekhar mass. If that value holds true, is coming out, that N is coming out to be negative. It means that the luminosity decreases with the Chandrasekhar mass. So this result was really interesting to us. And we have, since we have taken all the parameters in our MCMC analysis, like distances to all the galaxies in the calibrators and the anchor galaxies, and the slope and the intercept of all the Cepheids and MB2. So we have taken all those parameters. So I could not show all of the contours here, but they are all Gaussian. And we say here the most important, the parameters, and we can see the MB1 and MB2, there's significantly difference. And because of two MBs, two absolute magnitude of supernovas, one is more compatible with the Rees and the other is more compatible with Planck. And just by extremely low redshift transition, and saying, okay, there is a non-standard gravity, which we don't understand around present redshift, or say up to the redshift of 1, and which can actually tells us or resolve or alleviate the Hubble tension. And these are the distances to how the distance will change. So we can see here, because of the shift in the PLR, the distances to the galaxies have changed after the G transition. Before there is no difference, but after there is a difference. And these two parameters, MW and BW, which is the PLR slope and intercept, they have not changed because we are not changing anything in the anchor box. We are only allowing the transition in the calibrator box. So all the 4 parameters before, which is the distances to the calibrator galaxies, LMC and NGC 4258, and the slope and intercept of PLR exactly remain same. MB1, and we have MB1 and MB2. MB1 is compatible with MB, which is the shoes allowed MB, and MB2 is responsible for giving H naught, which is 65.90, which is more compatible with the Planck measurements. So Hubble constant tension is also related to the absolute magnitude tension. And we can see here that since by allowing 2 MBs, and it agrees and solves the Hubble tension. So now we are able to come from 73.73 to 65.90. And since we are doing in the low redshift, extremely low redshift, we don't have to even touch the BBN constraints or CMB constraints. So just by using simple physics, we can explain the Hubble constant alleviation or solution to it. So is 5% change in G, is that allowed? So I scrutinized and I checked, there are many papers from there. So from BBN, it says that when combining measurement abundances from baryon density, CMB, this much change is allowed within 2 sigma, 5% change is allowed from 2 sigma. Also from BAO, it is allowed, like 5% is allowed. Now, I have not explored till now. I wanted to, but I have not explored till now. What happens to the sigma 8 problem? Because all the cosmological tensions have to be solved in one, like it is a good model if we can solve all the tensions together. It's so we want that. So what happens to the sigma 8 problem when we actually change the Hubble constant or we allow G-transition? So this was a paper recently which appeared on just 5th of June, last week or something, last week. We see here that the Hubble constant tension is alleviated from large and 5 sigma to 2 sigma for varying m, and the growth tension can also be resolved after attributing the variation of n due to the modification effective Newton's constant. So maybe it is also a solution to the sigma 8 problem, and I think it is really interesting field we should explore about. So the conclusion from this work was the G-transition we proposed is equally favored. Sorry, I forgot to tell about this chi-square per degree of freedom. I have more degree of freedom here, but around there is same degree of freedom, chi-square per degree of freedom with and without transition. So without making the chi-square worse, we are able to solve the problem. So the conclusion is the G-transition is proposed is equally favored by the data over no G-transition. It solves the Hubble tension without taking any prior from CMB. This is a really big thing that we are not incorporating anything from CMB, and it gives us a lower value of H0. We also verify that supernova peak luminosity, non-standard gravity, no longer scales at Chandrasekhar mass, and it is already been seen in the observational supernova data, but it is inversely proportional, and we put constraint on that. We have claimed that CFID PLR breaks or maybe the intercept change after certain distance, and that may be the only cause of Hubble tension. So before moving further, this was more about cosmological tensions, and if we can solve the cosmological tensions, do we believe in early universe solutions or late universe solution? I was trying to do that using anomalies within low redshift and within high redshift. So using anomalies within CMB or within Planck experiment, or from low redshift, I was using, okay, what are the anomalies from in the standard objects like standard CFIDs, or what is in the data from supernova, is there an anomaly? And if I incorporate, what happens? Now, another third precise measurement of cosmology is BAO. And just on Tuesday, this paper appeared on arXiv, where I checked the consistency between 2D BAO and 3D BAO. Also, I included DAISY data set there. And also, we proposed that what are the future directions for both observationalists and theorists that can be done using the 2D and 3D BAO data. So is it a trouble for standard lambda-CDM cosmological model? So the data set that we use there are the standard supernova type A, and we used Pantheon plus whole sample, which is 1701 data points from redshift 0.01 to redshift 2.3. We have used 3D BAO from anisotropic, both anisotropic and isotropic measurements. And we use 2D BAO data, which is the 11 measurements using SDSS, namely DR10, 11, and 12. And the observables calculated using these data from supernova, we calculated luminosity distance, And sorry, we have the observational data for apparent magnitude of supernovas. We need to assume some value of m there, and just not to bias our results, we have taken m from low and high redshift measurements. So we have taken around 7 or 8 m values compatible with both Hughes and Planck, and we have taken model as lambda CDM. So just that our this paper is just about the 2 BAO data set and not about the model of cosmology or about the supernova data set. That's why the MB has been varied, like really incorporating both MB from preferred by Hughes and Planck. And also we have done most of the analysis in lambda CDM because we just wanted to compare BAO data set and not supernova at present, not the cosmological model at present. Another observable which we made from BAO is angular diameter distance and volumetric distance. And from 2D BAO, we have measurements of theta BAO. So now these were the inferred quantities like the distances, luminosity, angular diameter distance, or volumetric distance. But what are the measured quantities is the apparent flux magnitude or the ratio of distances by RD and not exactly the angular diameter distance or volumetric distance. What we measure is the shift or the dilation parameter in BAO. And in 2D, we assume we take measurements of theta BAO. Now, is there any fiducial cosmology in the BAO, or are they completely cosmological model independent? In 3D BAO, we have to have fiducial cosmology because we are measuring the shift from the fiducial cosmology. That is the actual measured quantity. We actually doesn't measure just the co-moving distance like transversal or parallel and perpendicular to the line of sight, but actually what we measure is the shift in the BAO from the fiducial cosmology. Same happens in the 2D BAO. What we are measuring is the bump. So what we are measuring in the bump is the shift in the bump from the fiducial cosmology. So fiducial cosmology is there in BAO, but how, and okay, it is assumed, and this parameter alpha is allowed to vary, but it is not allowed to go very far away from lambda CDM cosmology. So I really need to ask myself, the models that I'm trying to check there, like exotic models like negative cosmological constant or incorporating G-Transion effects, is this alpha wide enough? Is this alpha, is this fiducial cosmology involved in BAO? Is it wide enough to incorporate my new exotic models? So I really need to test that, and we need to see that. So the results that I got here is, okay, so since BAO measures the product of H0 RD, I wanted to plot the same. And just to say that my results are not biased by the supernova data or MB from supernova. So I have taken like 7 or 8 MB's values. So irrespective of MB from supernova, the H0 RD that we got here, so the black error bars are from 2D BAO data plus Pantheon plus, and the teal color error bars are from 3D BAO data. And we can say, okay, within less than 1.5 sigma, they are both compatible, H0 RD. 2D BAO gives a bit higher value of H0 RD, and 3D BAO is more compatible with the CMB. But within less than 1.5 sigma, they are both compatible. And these are the results from DAISY BAO. DAISY BAO also gives a value of H0 RD bigger than what CMB prefers or 3D BAO prefers. But I think within 1 sigma, 2D BAO is compatible with DAISY. And also 2D and 3D BAO agrees well with each other. So we can see here that this is RD H0 is around 100 and it's around 105. But within the error bars, they agree with each other. But when I plot, so this is H0 RD on the y-axis, but when I plot and see it in terms of in the contour space of omega m0 and h0 RD, and I plot 2D and 3D BAO data, I see more than 2 sigma deviation. So why is this happening? Okay, let me check. Is my h0 RD right? Let me just cross check. Yes, my h0 RD is compatible with DAISY, is having problems with CMB h0 RD. And if I plot the marginalized h0 RD plots, yes, they are compatible as well. But as soon as I involve omega m0 there, and I'm assuming lambda CDM model there, these two, the contours are having more than 2 sigma problem. So now, is it trouble to the standard cosmological model we assumed? I would say yes, but along with that, maybe this BAO fiducial cosmology that has been assumed in observations, that may also need to be changed, because it also is affecting how we infer from the data set that we have. I also included DAISY dataset, and I wanted to test about W0, WA contour and how compatible it with the lambda CDM. So I have the contours for 3D BAO and 2D BAO and DAISY, and I'm using here the shoes same MB just to not to bias like too many things, change too many things, and just change the BAO data. So we can see here there are bigger contours for sure from 2D BAO because of the bigger error bars. But lambda CDM is on the edge of the data at the 2 sigma level, and it is different from what DAISY have seen, is because they have using supernova sample around 1500 points, and I'm using all 1701 points. And so this is about the left contour. On the right contour, we can see here the 2D value of RD that I get here is higher because of the higher RDH values. So the RD value obtained from 2D BAO is compatible with the RD of Planck. But this is solely the artifact because the relatively higher product of H0 RD measured by 2D BAO and 3D BAO. So the main inference from this paper, if I would like to give, is I would like to conclude by saying what not to conclude. Okay. So on the x-axis, I have the value of H0, which I've given by incorporating a prior from supernova and by putting MB there, a Gaussian prior. And we can see here 2D and 2D BAO, I'm getting RD more compatible with Planck, even if I'm having low redshift H0. So the main inference from here is when we are trying to propose models for cosmological tensions, and we are saying, okay, I'm getting higher H and as well higher RD by using 2D BAO, we should really doubt that, because even within the lambda CDM, we see here that we get higher H0 and higher RD within lambda CDM. So if we don't consider what is happening to omega m0 and sigma 8 problems, I don't think that should be considered as a solution and trying to different model and saying, okay, this is the solution. So we should not really say that, because within the lambda CDM, we are able to see higher H0 and RD using 2D BAO data. So if we are using 3D BAO and saying, okay, we can take that, but using 2D BAO, it already measures the higher value of H0 RD. So we should try to understand what's more is happening there rather than just taking it as a solution to the cosmological tension. So final takeaway from my talk is precisely measured experiments like Planck and Hubble Space Telescope may need to relax or revisit the theory to solve the cosmological tensions, because till now what we have been considering standard are seeing anomalies. So maybe we need to revisit the theory. And the theory can be the calibration of distance ladder, recalibration, or the CMB polarization data, or there's some physics that is waiting for us to discover. And the question must be taken while concluding about cosmological tension, especially while using 2D BAO dataset. And my near future interests are, I'll be really interested in testing new probes and observations such as gravitational waves, GRB, pulsar timing arrays, 21 centimeter with the present theory that we have. Test standard assumptions of lambda CDM, like standard distance ladder and standard candles, exploring BAO alpha data sets by allowing bigger priors for dilation parameter. I also like to understand, can we see any hints of new physics while measuring galaxy temperature correlation? Also, it's very interesting to me to understand the arcade anomaly and if it can resolve the Hubble tension and how will it affect the Hubble tension, and something completely different, which may excite me that I'm working on that. And thanks.
Thank you so much for the very nice talk. Do you have any questions?
Hi, Ruchika.
Hi, Simone.
Thank you for your very interesting talk. I'm not sure. Maybe I would like to understand better, but the 3D measurements of BAO does not consider a model, or it's also model independent, because I thought that since 2D is model independent, it would be more trustful than 3D. But in this way, the way you present the results is kind of the opposite, right?
Yes, to what I understood by reading papers about 3D BAO and also DAISY and also 2D. I mean, I have written that in detail in the paper, you can check. But I think that if you are seeing this parameters, I mean, I think you must have seen this parameter, right? So RD fiducial. So RD fiducial goes into inferring the alpha perpendicular or parallel. So, I mean, we need to assume some cosmology when we are going away from redshift, right? So what we are measuring is in the terms of distances, and when we are converting it into the redshifts or vice versa, we need to assume some model of cosmology. Like, I mean, okay, we can allow bigger priors, and I mean, it was explicitly written in the DAISY paper that these alpha values are not moving very far from lambda CDM. Okay, and I can show you the paper. But and also in theta BAO, what we are trying to do is we are just trying to project the 3D measurements into 2D. So it's like just an imprint of 3D measurements into 2D. How do they look? So I think they are also having fiducial cosmology. And I've written in the paper in quite detail, like exactly where the fiducial cosmology goes. I mean, I may not be having everything in the paper, but I tried to write quite a bit, like where is actually the fiducial cosmology goes into the picture. Like, because in 2D measurements, what happens is because of different parameters and systematics, there are various theta bumps, okay? And to find the true bump, you should know what is the expected theta BAO. So you try to marginalize or smooth out all of the bumps by having close to the true theta BAO, which is your expected theta BAO from the fiducial cosmology. So I mean, I think both of them are having fiducial cosmology.
Okay, thank you.
Thank you. Lakshmi Priya.
Hello, thank you for your nice talk. I have 2 to 3 questions. In one of your slides, you said something sigmoid tension, and you have given a paper there. And you said this problem is, if I understood correctly, you said this problem is solved or something. Is that problem is actually solved or still it is going on?
Okay, so this paper just came last week. I've not read it in quite detail. So I cannot say right now about sigma tension, but reading about abstract and conclusion, it seems that it actually elevates it. But I need to read that paper in quite detail. I agree with you.
Okay, thank you. And another question is, when you explain the pulsation of seafood, there are like double helium and the single helium. Yeah, so you said there are more free electron in the double ionized helium, and there is contraction and the expansion. But I didn't understand quite well why this contraction happening.
Okay, so it's like when it is small, because everything is in a very small volume, it is more dense, right? So it is more hot. And naturally, it will start to expand because it is hot. And its volume will increase. And by itself, it starts to get cold because of the expansion. But it cannot be keep expanding, right? And at the situation where it is a bit bigger, since it is more cool, it turns into single ionized helium by capturing an extra electron. But it cannot be keep expanding always. So it will again
Yeah, like
contract.
why it is cannot keep expanding always? What is the reason?
Because, okay, there are two forces, right? One is like gravity and one is the pressure.
Yes.
So they are trying to balance each other. So it will start to become more bigger, but then it will again start to go back because of the gravity, right?
Okay, yeah. You are saying gravity is pulling inward, then that's why it's contracting, right? Okay. Okay. Another question. When you said there are when we change the redshift, or maybe for an example, there is one slide when you choose epsilon equals to 0.2 or epsilon equals to 0.32. Yeah. Previous slide.
Yeah.
Yeah, here. So when you change the epsilon value and you add some other data, for example, JWST or low L, then there are higher values of higher value of the change in chi-square. Okay. So okay, so you are adding something and you are getting some different values, but do you observe why after adding something the values are drastically changed? What's the reason behind it?
Okay, so firstly, all of this is having JWST along with it. Just to say that, okay, you were saying some of are having JWST, all of them are having JWST. And for this epsilon 0.2 value, if we add low E, the value drastically changes. Yes. Now, there could be many reasons to that. And that we try to understand. The reason can be that there's something different in the CMB polarization measurements because it measures this low E polarization and that constrains the tau parameter. So this is one of the explanation we are trying to give.
Okay.
For why. I mean, we don't know exact reason, but okay, one of the explanations would be like that.
Okay, thank you.
Yeah.
Thank you.